So today we're going to carry on with our discussion on quantum states. We've already looked at a basic quantum interferometer, an interferometer that encapsulates most of the ideas that we have about quantum interference, quantum computing, measurements, complementarity, the incompatibility between wedge path and interference, the incompatibility between position and momentum, probabilities, probability amplitudes. We also got introduced to the notation of Dirac, that is the Bloch notation. All of this started to come to life, as if a new plant is taking its shoots out of the soil. I mean, this was probably your first encounter with all of this. So now we're going to go a step further. So in any computing paradigm, you have states which are Boolean zeros, ones, bits, and then you do some transformation. And those states change. The transformation is called an algorithm. You implement an algorithm, it transforms the states and you get an output. So the general simplistic model, the circuit model as it is called, is that you have a computer or an information processor. You input certain states come in, and certain states go out. And the information processor acts on these states to give you new states, perhaps. So in classical Boolean logic, the input states could be a sequence of zeros and ones, and the information processor implements an algorithm, and you might get a sequence of output bits or states. So now the same kind of idea carries over to the quantum domain, in one form of the quantum domain. So you have some input states, psi, and they go through a box, generally called a quantum computer or a quantum information processor or a quantum communication channel or a quantum transformation, and then you get some output states. Let's denote those output states by psi with a prime sign on it. And all of this processing is mostly quantum mechanical. And these states are quantum mechanical states, quantum states that can exist in superposition, and then you have some device that measures these quantum states, and possibly you might collapse some of these states. So this is one model of quantum computing. There are other models of quantum computing, but this is the simplest thing that I can talk of. So in order to build a quantum computer, you would need to initialize your states. You need some kind of initialization. You would need to have a physical model that can start off your computing in a particular state. Just as if you would like to initialize a register in a sequence of bits. So you must initialize quantum states. And by the way, initializing quantum states might not be an easy thing to do. And quantum states have their own properties. You cannot copy states. There is a no cloning theorem that we will prove that shows that quantum states cannot be copied. They cannot be cloned. They cannot put in a photostate machine and make replicas of the state. Then you need some kind of transformation. Transformation could come up with different names. You could call it an operation, a quantum gate, the unitary operation. Then you should have the ability to measure your states. And measuring, as you know by now, is not a straightforward thing in quantum mechanics. It collapses the state, it changes the state, and you will have to repeat the experiment a multiple number of times to find out the probability amplitudes. So you get probabilities at best. From those probabilities, you have to work your way backward and find out the coefficients for the amplitudes, the probability amplitudes in the state. So you need three ingredients: initialization, transformation, and measurement. And the quantum world is a nasty world, nasty world, because you deal with small objects generally, electrons, protons, neutrons, ions, molecules. Generally these are small things, and generally some of the quantum effects only manifest at really low temperature, close to 0 kelvins. So whenever there is, if you have a resistor, right? Everyone knows what a resistor is. You put a voltmeter across a resistor, would you get something? Just a resistor and a voltmeter? Would you get some reading?
No.
What do you mean by no? What will your voltmeter show?
0.
There's no such thing as 0. It will show some noise, some crackle, some noise. That's called Johnson noise, because the electrons in the resistor, they are showing Brownian motion because they are at a finite temperature. So you put a voltmeter and look at it in an oscilloscope or record the data. This is your time. You will measure some noise, right? This noise is called Johnson noise or thermal noise, and its RMS value is proportional to 4 Avogadro number, the temperature, the resistance that you're trying to measure, and the bandwidth of measurement square root. So it's a precise amount of noise that you will measure. So all of this noise is also here in a quantum computer. So you're trying to measure something in an information processor, you're dealing with electrons, and lo and behold, there is some environmental factor that is trying to destroy your state even before you've done a measurement. Quantum states are really fragile. They interact with the environment. The environment actually measures the state instead of having the observer measure the state. This phenomenon in which there are external disturbances that change the state and to an undesired or an unintended configuration. Those external disturbances are called decoherence. So if you would like to build a quantum computer, all of this takes time. So you input a state, there is a time course that is running. Nothing happens instantaneously, even in a very fast microprocessor. It takes time. So over the time scale of the experiment in a quantum computer, you need to mitigate or protect against those errors that are caused by this unwanted influence of the environment that is called decoherence. So that's why it's so difficult to build quantum computers, because they take a finite amount of time. Over that finite amount of time, decoherence creeps in and destroys your states. So that's why it's so difficult to build quantum computers. They have to work in a really nice, pristine, pure environment, very cold. You have to do all kinds of things to protect against decoherence. And sometimes errors are inevitable. So when errors are inevitable, which means they are bound to happen, they always happen, you have to have some mechanism of diagnosing errors and correcting them. So decoherence goes hand in hand with quantum error correction. The computer scientists learn a lot about error correction, but this is truly of a different league, quantum error correction. So you have all of these ingredients that are necessary to build a working quantum computer, or a quantum communication system, or a quantum channel. And the other thing is, all of this is useless if you cannot scale it up. Scaling it up means, talking about qubits, it might be easy to do all of this for a single qubit, but you won't be able to do anything interesting with a single qubit. You need 5 qubits, 10 qubits, 100 qubits, and there is a threshold that many technologists have devised, which is called the quantum ascendancy limit, which is at about 100 qubits. So you need to surpass this holy grail of 100 qubits to do something useful. So everything has to be scaled up as well. So these criteria for building a quantum computer, generally they are called, these are 5 criteria, they are called the De Vincenzo criteria in honor of the name of the person who proposed it, De Vincenzo's criteria. And the other thing, sometimes some people would say that it also have another requirement, and that is, once you do something at a quantum computer at one location in space, you have to transmit that information to another point. Sometimes you need flying qubits as well. So that adds more complexity to the mix. So from a technology perspective, and that is what is driving this field, you need to satisfy these criteria. And what we're going to talk today about is, we've talked a little bit about states. We've talked a little bit about initialization. We've talked a little bit about measurement. Now we're going to talk about transformations. And we've already seen transformations done by a beam splitter in a maps and interferometer. So we've already encountered a transformation. Okay, so we're going to talk about quantum transformations today, or quantum dynamics. आपके सवाल पूछें।
सर, हम एल्गोरिथम या मॉडल के बारे में, इसको बिल्ड करने के बारे में तो बात करते हैं, क्वांटम कंप्यूटर बिल्ड करने का क्या मतलब है? Build a quantum computer.
I think if you have to build, computer is a piece of hardware, right? So take certain states, output certain states. So how do you build it? I mean, what does it physically look like? You have to build it up.
So we will make some hardware design?
Right. So it's a piece of hardware, it's a piece of tangible, some instrument that is qualified as a quantum computer. In the example that I gave in the previous lecture, you had laser beam, shining photon, then you have a beam splitter and mirrors. It's a piece of hardware. You have to build that. So now let's look at quantum dynamics. So we have states, and then they undergo certain dynamics in this box, and states are transformed. Right? Alright, so and let's look at our Bloch sphere again, on which quantum states of a single qubit live. So the single qubit quantum states live on the surface of the Bloch sphere. So there is, say, ket 0 living here, ket 1 living here, and let me just draw, for the sake of convenience, these axes, this x-axis, a y-axis, a z-axis. It's not a real Cartesian axis, just for illustrative purposes. And a state that lives here could be is ket 0 plus ket 1, superposition state, and so on. And a general state here with an azimuthal angle phi and a polar angle theta, as you recall, is given by this general form cosine theta by 2 ket 0 plus sine theta by 2 e raised to I phi ket 1, where theta and phi are real numbers. And you can always, as I mentioned, always add a global phase to this. So this will be the same as if you add some global phase with the entire state. Physically, from the measurement perspective, these states are indistinguishable, because you project them onto some measurement basis and take the modulus square, this phase factor just washes away. But when you take the complex conjugate, this multiplies with this complex conjugate to give you 1. So this just withers away. So this is our understanding of the Bloch sphere. All the quantum states of a single qubit live on this sphere, on this hypothetical abstract sphere. And these states need two basis states, ket 0 and ket 1. These are the basis states, right? So everything is described in this basis. And there are other basis states possible as well. We'll talk about that. Now what did a beam splitter do? A beam splitter for example, a beam splitter did the following. It took ket 0 and converted this into ket 0 plus 1 under 2, and it took ket 1 and converted this to ket 0 minus. All right. So now if you just look at this transformation, if we were to look at this transformation, then let me redraw the Bloch sphere in a minimal fashion. You're starting off here, ket 0. And the transformation, the beam splitter effects is that it takes this input state and creates this. So where is this final state on the Bloch sphere? It's on the equatorial plane right at the x-axis. So what this beam splitter has done is that in a sense it has taken this state and moved it on the surface of the Bloch sphere, and you end up on the equatorial plane right in an axis pointing towards you, which we call the x-axis, and your final state is now this thing here, ket 0 plus ket 1 over under 2. Now what kind of geometric transformation is this? What's happening here? So there are different kinds of geometric transformation. You're standing here, one geometric transformation can translate you. One geometric transformation can twist you. One transformation can shear you. Another transformation can rotate you on a plane. So what kind of transformation is this? It's a rotation. Good. It's a rotation. So the beam splitter is doing a rotation on the Bloch sphere. Quantum states are being rotated. Now, we are fond of mathematics, so every rotation, let's denote a rotation by r. Okay? And since it's an operation, let's put a small hat on top of it. This is quantum jargon. Now this rotation, what do you need? So how big is this rotation? The question, simple question, how big is the rotation? 90 degrees. Is that all you need to tell? About an axis. So you need to tell about the axis, about which axis is the rotation taking place, and you need to tell the amount of rotation. So there are two things that you need to inform the reader or the person who's learning this subject. You need to inform him or her about the axis of rotation and the amount of rotation. So the axis of rotation here, what's the axis of rotation here? One axis, it could be the y-axis. So I have to specify this, r sub y. And then I need to tell the amount of rotation, which is 90 degrees. So rotation of 90 degrees about the y-axis when acting on the state ket 0. This is the transformation that the beam splitter is doing, creates a new state ket 0 plus ket 1 over under 2. And if you started off here, ket 1, what would this transformation do to ket 1? It will move on the other side, on the dark side of the Bloch sphere, which is behind you, and move back at the minus x-axis. So you'll end up here. Right from the periphery, from the back. So if you're using a convention of the right hand rule, you point your axis in the direction of the axis, your fingers will be curled. If this is positive, the fingers will be curled in the positive direction. So the beam splitter is really doing, in the Bloch sphere sense, a 90-degree rotation about the y-axis. Yes, sir?
So ये जो right hand rotation है या जो direction of rotation है, that in itself एक information ही जो provide करनी चाहिए.
So you have to conform to a certain convention. But then you have to define, okay, I define this to be cat 0, I define this to be cat 1, I could also define this to be cat 0. So you have to work with some axioms, some basics, and that's given. This is the convention that we're going to follow. If you change the axis of rotation, put a minus sign here. Okay? Yes?
So how do you know that beam splitter does this thing, right? Ket 0 plus ket 1.
So yesterday we saw, in the previous lecture we saw that the beam splitter is creating a superposition that is coming out of the experiment, and this is how you're describing it.
लेकिन आपने ये उस वक्त भी ये डायरेक्ट लिख दिया तो फिर कैसे माइनस और प्लस कैसे आता है? यानी आपको कैसे पता कि ket 0 पे ये अमल होगा? Ket 0 plus ket 1 over.
So how do you know that the NOT gate inverts the state? How do you know that? Because that's how you define the NOT gate.
Yes.
So that's how we are defining the beam splitter. And the beam splitter is engineered and manufactured in such a way that it does that. Okay. So what a mirror does, it reflects light, it adds a phase to it, possibly a pi radians phase shift. So that's what different elements do. Yes.
Sir, can we have a quantum state outside this sphere?
Can we have a?
Quantum state outside this?
You can have inside, but I can't think of anything outside. States can exist inside the Bloch sphere. They're called mixed states. We're going to deal with them later. Yes.
Bloch sphere में outside उसकी surface भी होती है, inside भी होती है.
Inside भी होते हैं, लेकिन वो अभी हमने वो states पढ़ी नहीं. They are called mixed states. Right now we are only dealing with states that live on the surface, and those states are called pure states. And why are they called pure states? We'll learn later. So everything has to come at its proper time. Alright, so a transformation can be described by some kind of rotation on the Bloch sphere. So now let's look at a few gates, quantum gates, logic gates. The first gate I would like to expose to you is a NOT gate. And the quantum NOT gate will have a certain truth table. Say input ket 0 goes to ket 1, input ket 1 goes to ket 0. Alright, so now let's see, I will give you 2 or 3 minutes to draw on a Bloch sphere what this transformation corresponds to. So draw a Bloch sphere and identify to me what the rotation is and write the symbol for that rotation as I've done over there. So that transformation has to work for both inputs. You need to come up with a rotation that works for both inputs. What axis? What axis do you get? So that's the question. Yeah, that's the question. Okay, this is one possibility. Right. Alright, so most of you have come up with the idea of a 180-degree rotation about the y-axis. So I draw the y-axis. This is my x-axis, the y-axis. And then if I were to do a 90-degree rotation about the y-axis, a 180-degree rotation about the y-axis, it will take this input state and bring it to the southern hemisphere. So far so good. If I were to have this as my starting state ket 0, it will go all the way back and end up here. So any disagreements with this? So this is the y-axis. If my state is here, it has to go back all the way to right. So this is my axis of rotation. This is my axis of rotation about which rotation occurs. Now, is this the correct transformation when drawn on a Bloch sphere? Any disagreements with this? Yes.
So the one on the equatorial plane would not be, it would not, the knot would not work for it.
Which one?
If there is a state on the equator.
Alright, so very good. So if you start off with the state ket 0 plus ket 1, which lives on the equatorial plane, if the NOT gate acts on this, so let's call that NOT gate U naught, right? So U is just a symbol for an operation. I'll explain why it is U. So what would happen to this state? Now this state lives here. What should really happen to this state? Just forget about the Bloch sphere picture. If you were to apply a NOT gate, what should happen to this state? It should remain preserved. Your answer, because ket 0 goes to ket 1 goes to ket 0, and they flip amongst one another. So you will still end up with the same state. So this state is invariant under the NOT gate. It's invariant under the NOT gate. It does not vary under a NOT gate. Does this kind of scenario look similar to something that you learn in matrices or linear algebra? When you're going too far. Eigenstate. So this, if this were a matrix, this state were an eigenstate of this matrix because it leaves the state unchanged. So that's my first motivation, that this quantum state must be represented by a vector and this must be represented by a matrix. Kets are represented by vectors and transformations are generally represented by matrices in their simplest form. Now if this were the case, your 180-degree rotation about the y-axis will not work because this is going to take this thing, ket 0 plus 1, and move it all the way back to here, and you will end up with ket 0 minus ket 1. So 180-degree rotation about the y-axis does not work as a NOT gate. So what works then? No. What will work? What axis do you need to choose, or what angle of rotation do you need to choose? So you need to choose an axis that coincides with this state, because this is an eigenstate. So if you do a 180-degree rotation on the x-axis, that works all the time for any input state. So your transformation, if it would be devised in a universal fashion so that it works for any kind of input state, not just the basis states, but any superposition of the states, it should have a general description. And the general description that qualifies for a NOT gate is R, a rotation of 180 degrees about the x-axis. So this will take any state and create its and do a NOT gate on it. Alright, and it will leave states that lie on the x-axis unchanged, because that's what a NOT gate does. So a NOT gate has some eigenstates, and these are the states ket 0 plus minus ket 1. So the eigenstates of a NOT gate, quantum NOT gate, are ket 0 plus minus ket 1 over under root 2. These are the two eigenstates. Now we can describe our states by vectors and the transformations by matrices. Now there's some liberty in choosing this. And why do we want to transform it into vectors and matrices? Because when we want to do a simulation of the quantum computer on a classical computer, or write an algorithm for this, or want to understand the subject, we need to do this on a computer, and the computer understands linear algebra pretty well. So what we could do is, we could define ket 0. So this shows that I'm making a definition here by a column vector. I can define this by a column vector that has 1 in one position and 0 in the other. And I can define the other basis state, ket 1, by another column vector, 0 and 1. Right, so I just flip the position of the 1. And my rules for inner products. So if I want to see how this rule is implemented in matrix form, for the ket, I still have the column vector. For the bra, I draw a row vector. I make a row vector. And if the entries are complex, I also complex conjugate them. Right now, if I do this matrix multiplication, my answer will be 1. As it should be for the inner product of ket 0 with itself, or ket 1 with itself, the inner product of ket 0 with. So these are two orthogonal vectors, by the way, right? They are orthogonal vectors in the matrix sense as well. So in this definition, what would my state, let's call this state, let's represent this state by ket x. Choose any label we like. So how will ket x be represented in this definition, in this basis? So now we are representing, note the word representing. We're representing a physical quantum state, ket x, in a particular basis. So what is the basis representation of this state? So it's a superposition of 0 and 1. This is this state. How will it be represented in this basis? 1 plus 1. So there's a 1 over under root 2 here and a 1 over under root 2 here. The general state, this side on the Bloch sphere, will be represented by cosine theta by 2, sine theta by 2, ei5, and so on. So now this is how we are representing quantum states in matrix notation. Got it? Now, once we have defined states as vectors, kets as vectors, column vectors, bras as rows, we would also like to define or write a representation of matrices of the unit of the transformations. Okay? So in this description, if you look at this truth table, from this truth table, can you come up with a way of writing down the matrix for the transformation and how big will it be? First of all, let's decide how big will it be. What will be the dimensions of this matrix? It's going to be a 2 by 2 matrix, right? Because it acts on a 2 row 1 column vector to give another 2 row 1 column vector. It has to be compatible for multiplication. So can you just by eyeballing? So now I'm going to represent this matrix by U0, right? And it's equal to a transformation, but to a rotation. I'm going to come to that in a point. So now what I would like to do, I would like to write a matrix, 4 elements, that describe the operation of this NOT gate. So can you help me populate these 4 elements? So what goes here? 0. Here?
1, 0.
So when this acts on, so when U0, I'm going to do it only once. When U0 acts on ket 0, this thing acts on ket 0, I would get this output, which is ket 1. So U naught acting on ket 0 must give me ket 1, and this matrix indeed does this operation. Oh, sorry. So one easy way of looking at this is, you look at this matrix, look at its first column. The first column is the output when you feed in the first input state ket 0. So when you feed in ket 0, the output should be ket 1. So you write the representation of ket 1 in the first column. When your second input comes in, ket 1, your output is ket 0, so you write the prescription for ket 0 in the second column. And of course you need to decide on an ordering. So when you communicate this with another co-worker, you will have to describe to him or her the ordering that you're using. You're using ket 0 in first position and ket 1 in the second position. So this is a NOT gate. And it turns out that if I were to look at a rotation about the x-axis through pi, this will be the same as a NOT gate up to a global phase factor. Let me explain this. All operations, most operations which are the simplest to understand, they are called unitary operations for a reason that I'm going to explain in a minute. All unitary operations can be represented as rotations on the Bloch sphere, and they're defined by an axis of rotation and an amount of rotation. So for any rotation you need to define an axis. This is your axis. The axis is really a vector, and you need to define an amount of rotation, say beta. Alright, and if you, this U0 gate will actually be equal to this. This is another symbolism for the U0 gate. But why are they called unitary gates? Because they are unitary matrices. Unitary matrices have a special property, and that property is that if you take the inverse of this matrix, every matrix has an inverse, this matrix equals U dagger. Where U dagger, what is dagger? U dagger means you take the complex conjugate of all the entries and transpose. So why are rotations unitary matrices? That's something we have to prove. Any questions up to this point? Yes.
सर जो हमारे पास रोटेशंस थी along the y-axis 180 degrees वो क्यों नहीं acceptable थी?
क्योंकि they will not work for equal superposition of zeros and ones, because what they would do, if you take a 180 degree rotation about the y-axis and act this on a ket 0 plus ket 1 over under root 2, just looking at the geometry you will end up with ket 0 minus ket 1 over under root 2, but that's not what a NOT gate does. The NOT gate by definition preserves this state. So you shouldn't end up with a minus sign here. That's why a NOT gate is legitimately defined by a 180 degree rotation on the x-axis only.
So you do 180 degree rotation around the x-axis because still it's because 0 से 1 comes.
Right. The question is that how do we represent this 180 degree rotation on the x-axis? So now this is my x-axis, right? It's basically pointing towards u. So I start off with this state ket 0. This is my ket 0. This is my x-axis. Now what I would like to do is I would like to do a 180 degree rotation of this axis of this state. So this is my axis, 90 degrees, 180 degrees at the back, right? So this state is moving all the way ending up here. You start off with this state, it's going to end up here. If I were to draw a meridian plane and I were to start off with this state, it will end up here. So the NOT gate can have any input. So it's a universal gate. It is oblivious of what kind of input is fed into it. And the matrix form and the proper axis of rotation should work for any input state. Yes? Yeah, it will work, but somehow you need to restrict that this NOT gate never takes superpositions. So that's contrary to the spirit of parallelism and using superpositions properly. So these gates need to be universal. Universal gates mean they work for any input states that you like. Yes?
Sir, does all the quantum states exist simultaneously on the Bloch sphere at a given time?
What do you mean?
मतलब कि जब हमने cat 0 को ट्रांसफॉर्म किया, that means टॉप के ऊपर cat 0 नहीं रहा, तो बॉटम में जो पहले से cat 1 था।
देखो ये था क्यों नहीं है, था है नहीं है. These states are represented on the Bloch sphere. So if you have a quantum state, you can pinpoint a certain location on the Bloch sphere and you can say that this state lives there. It's an abstract notion. Once a transformation has occurred, your state is living on another point on the Bloch sphere. So every qubit can be represented by some point on the Bloch sphere. And of course it all takes time. No unitary operation happens instantaneously. It takes time. So there's a time dimension to this. We're going to cover that when we link this up with the Schrödinger equation. Because the Schrödinger equation has time in it. Alright, so let's move on to, say, another gate. So I want to define a gate called a Hadamard gate. Hadamard gate. And so maybe this to be given as a home. What the Hadamard gate does is that it takes cat 0 as an input and outputs a superposition 0 plus 1. And it takes cat 1 and outputs cat 0 minus cat 1 over under 2. Alright, so now let's suppose that the unitary operator for this is U Hadamard. First of all, in this basis that we've chosen, let's call that basis. So I don't want to point out to that basis again and again and again and again. So I call this basis, this representation, the Zeeman basis or the computational basis. Okay? Now in this basis, just by looking at what happens to this input state, which is the basis state, and what happens to this basis state, which is the orthogonal basis state, can you write down the matrix for the Hadamard gate, please? I just want to put 1 over under 2 out, factor it out so that it's easy to write.
1 1
यहाँ पे 1, इधर क्या?
1 1 minus 1.
This is the representation of a Hadamard gate. What the Hadamard gate does is that it creates a superposition. It creates a superposition. So the U Hadamard acts on cat 0 and creates a superposition. It acts on cat 1 and creates another superposition with another phase in between. And this is the form. Now why is this called a Hadamard gate? Because a matrix of this kind, in which all the rows are orthogonal to one another and all the matrices are orthogonal to one another, they're called Hadamard matrices. And you can write 4 by 4 Hadamard matrices and so on. So just tensor products. I'll talk about tensor products later. But this is a Hadamard gate. Now, can you please attempt to describe what the rotation matrix looks like? What's the axis of rotation that legitimately describes this operation? What's the axis of rotation and what's the amount of rotation? I gave you 2 or 3 minutes to think about it. About what? So the question is, what rotation operator does this correspond? About y-axis, how much is the rotation? 90-degree rotation on the y-axis, correct? Is that correct? So don't fall into the same trap. Along? No, z-axis wouldn't work because z-axis is this axis. So any rotation, so if you start off with cat 0 is already on the z-axis, it will not rotate. So z-axis is this axis, so rotation on this axis, it will do nothing for cat z. So now these gentlemen have come up with this idea of a 90-degree rotation about the y-axis. So what this does, it works for cat 0, brings it here, which is 0 plus 1 under root 2, which is fine. That's required. It takes this state, which is at the southern pole, cat 1, and brings it back on the further side, brings it back here, 0 minus 1 over under root 2. So it's working for both of these basis states. But what if I do the following? I take cat 0, I apply a Hadamard gate on it, I get cat 0 plus 1 over under root 2. What if I do another Hadamard gate on it? What if I do the Hadamard gate twice? So I put 2 Hadamard gates in tandem. So I have one Hadamard gate and then I follow it in quick succession with another Hadamard gate. So what should I really get if I follow this truth table? I should get cat 0, which means that the Hadamard gate done twice is identity. So this matrix has the property that if you take this matrix, square it, I should get identity. Which means that the second Hadamard gate is undoing the action of the first gate. So the Hadamard gate is itself inverse. So one Hadamard gate is the inverse of itself. That's a property of a Hadamard gate. It's itself inverse. So this rotation actually does not work for this input state. Because if this were your input state and you were to do a 90-degree rotation on the y-axis, this cat 0 plus 1 would really get to cat 1, which is not desired. So is there any other rotation that you can think of which works? Just think about it. Just use your choreographic skills, geometric skills on a sphere and see if you can come up with an axis of rotation and an amount of rotation that really works. You do it twice. So you start off with the north sphere, the north, end up here, and then you do another Hadamard gate with this input state, you get back here. Around x-axis, no, that's not gate. क्या एक्सिस ऑफ रोटेशन क्या है? So you do 2 rotations, one after the other. So you do a 90-degree rotation about y, followed by a 180-degree rotation about x. So if I do a 90-degree rotation about y, followed by a 180 degree rotation about x, you end up here. So let's see if this works for here. So you start with this state, a 90 degree rotation about x will get you nowhere. But a 180 degree rotation, 90 degree rotation about y will get you here. But a 180 degree rotation about x will then get you back here. So let's see. So you're saying that I would like to do a 90 degree rotation about y, correct? Followed by a 180 degree rotation about x, right? And see the manner in which I've written these rotations. First I've written the rotation on the right, which happens first, and then I've written on the left the rotation that happens second in time ordering. So the time ordering works here because your states are here. First this operation acts followed by this operation. So if I were to do, let's start off with this state. If I were to do a 90 degree rotation about the y-axis, this state will come here. And then I did a 180 degree rotation about this axis. This state will move along this meridian plane and end up here. Correct. Now will it work here? That's the question. Will it work here? So if I have a ket1 as my input, ket1 as my input, I do a Hadamard, I get ket0 minus 1 over under root 2. Then I do another Hadamard. What should I end up with? Shouldn't I end up with ket1?
Yes.
I should end up with ket1. So let's see if this sequence works. So I start off with this state. I do a 90 degree rotation about y. I end up here. And then I do a 180 degree rotation about x. This is on the x-axis, it goes nowhere. So your prescription does not work for this input state. It's a nice attempt, but it doesn't really work. Kisne bataya tha? Good attempt. So you're doing composite rotations, one after the other, but they don't work. If I were to put a third rotation with it, actually it will work. Do another 90 degree rotation about y after this. It's going to work. Anyway, one rotation I can always come up with. You know this idea of Euler rotations? Any rotation on the Bloch sphere, if you do one after the other, can be represented by one rotation, one axis of rotation and one angle of rotation. So if I were to give a shot to this, if I were to use as axis of rotation, which I am now representing by this big solid line, and this axis of rotation is actually on the xz plane. So my axis of rotation is now no longer on the x plane, it's no longer on the y axis, it's no longer on the x axis, it's no longer on the z axis, rather it's in between. This is my x axis, my z, it's in between at 45 degrees on in the xz plane right here. And if I were to do a 180 degree rotation about this, I will have the state move in a cone and get here, and I repeat this, I will go back. So if I am a clever artist, which I am clearly not, let's attempt to draw this. So my state starts off here and a 180 degree rotation about this axis. So I move somewhere on the opening angle of a cone, end up here. I end up at ket 0 plus 1. And if I were to do it again, I will start off with this state, now do a 180 degree rotation about this axis, I end up here. So it's like a 180 degree rotation about this, like, so the state is coming here, and then I have to twist my arms a little bit. This is my axial rotation, I'm starting off here and coming back here at the North Pole. So I'm moving on the opening locus of a cone. So a Hadamard gate really is a 180-degree rotation about the strange axis. That axis really is neither x nor z. It's kind of x plus z over under root 2. Over under root 2 because this is cosine 45 and sine 45. So about a twisted axis, tilted axis. So the Hadamard gate is a 180-degree rotation about a tilted axis. You could also do rotation about the z-axis. Alright, so any questions about the Hadamard gate? We've seen the NOT gate, we've seen the Hadamard gate, and we've written down the matrix forms of these gates, and we've written down the Bloch sphere representation of these rotations. Now, one last gate I would like to talk about is the phase gate. It's important. What the phase gate does is that it takes as input ket 0, does nothing to it. It takes input ket 1 and really does nothing to it, only adds a phase. So first of all, what's the matrix for this operation? 1, 0 needed for it, right? So how do we represent this on the Bloch sphere? Right, so you can do a rotation about the z-axis. So this is my z-axis, this is my ket 0. Ket 0 lies on the z-axis, so nothing happens to this. But ket 1 also lies on the z-axis. Is there anything happening to ket 1? No, it's just picking up a global phase. I think we need to change the battery, just a minute please. Battery bajna. Alright, so this global phase doesn't matter. But what if I input ket 0 plus ket 1 to the phase gate? Ket 0 remains where it is. Of course, I need to normalize. And ket 1 picks up a phase. So this is indeed represented by a rotation. So I start off here, I'm moving, twisting around the z-axis. So I'm moving here and end up at certain time here at this location, which is precisely this state. So now this is your first encounter with a complex number inside, and though it might look trivial that ket 1 is not changed, having this phase factor does allow for superpositions to take up all these strange relative phases. So we've looked at 3 gates. We've looked at a NOT gate, we've looked at a Hadamard gate, and we've looked at a unitary gate. A phase gate. Now all of these matrices that we've written are unitary. Rotation operators are unitary. Now what does that mean? In order to describe unitarity, so remember, in single qubit quantum computing, that's all you need to know. You need to know how to represent states, and you need to know how to represent rotation operators. Rotation operators change states. Now it's another question, how do we implement rotation operators? In a real quantum computer, it depends upon the technology and the platform that you're using. But in order to describe unitarity and rotation operators, we need to describe another class of matrices. And these matrices are called the polymatrices. Polymatrices. And the polymatrices are given by these three beasts: a sigma x, which is 0, 1, 1, 0. This is just a definition. Sigma y, which is 0, minus iota, iota 0. Sigma z, which is 1, 0, 0, minus 1. Alright. Now let's suppose armed with this definition, first of all you will observe the property that you take any sigma I, square it, I think you get identity. Another property I think is that if you were to take the commutator of sigma x with sigma y, I think you get 2 iota sigma z. Commutator means, so a commutator of two matrices is defined in the following fashion: AB minus BA. Now a rotation operator, say about the x-axis, through some angle, say beta, is given by exponent e raised to power minus I, this angle beta, the amount of rotation, and the poly operator corresponding to the x-axis with a 1 over 2. I think this is as far as I recall. Now how do you take the exponent of a matrix? So you need to find out what the exponent of a matrix is. Likewise, if I were to take the rotation about the y-axis through some angle beta, this would become E minus I beta sigma y over 2. RZ beta would become E beta minus I beta sigma z over 2. A NOT gate, we've argued, is a pi rotation about x. So this would be E minus I pi sigma x over 2. Now, how do we solve this? Is this a matrix? This must be a matrix. But here we have a matrix which is exponentiated with some factors and an iota. So how do we find the exponent of a matrix? So we have to resort to some mechanics here. Or some matrix mechanics. So one theorem that I would like to present to you is the following, and this is a very useful theorem. By the way, Abdullah, please make one homework question about, can we come up with 3 rotations about 2 different axes that will do the same thing as a Hadamard gate? Alright, so a theorem I would like to mention is that if I have e raised to power minus I theta A, some operator A, some matrix A, this is equal to, so I put a plus sign here or a minus sign here, cosine theta identity plus minus iota sine theta into A, if A square is identity. This is a theorem. If this matrix has a property that its square is identity, which means this is what is called an idempotent matrix, then this holds true. If theta is a real number, this would hold true. You could actually prove this by the Maclaurin series. So you already know what the Maclaurin series is. E theta is 1 plus theta square over 2 factorial plus theta cube over 3 factorial and so on. So just take this to be a matrix here. A square is identity, A cube is identity, A4 is again identity, and you also know the expansion for cosine theta and sine theta in the Maclaurin series. You can actually prove this, that this holds true. Now if you look at this operator here, let's use this theorem to see what the form of this matrix looks like. On a rotation about the x-axis through an angle beta is given by exponent minus I beta sigma x over 2. Now sigma x has a property that its square is identity. So we want to put this half factor with beta. So this is e raised to minus I beta over 2 sigma x. Now apply this theorem. I will get cosine beta over 2 identity minus I sine beta over 2 sigma x. And if I want to put this in matrix form, this becomes cosine beta over 2. This is minus I sine beta over 2 here. This would be plus again minus I sine beta over 2, because sigma x is just a 1 here and a 1 here, and this will become cosine beta over 2. And if this angle were 180 degrees, you put beta equals 180 degrees, this becomes 0. This becomes 0. This becomes minus iota, this becomes minus iota. So I have 0, minus iota, 0. Is this the same as a NOT gate? You argue that a NOT gate is somewhere over here. This should be a NOT gate. 0, 1, 1, 0. So that was your educated guess. So you thought that the NOT gate should be 0, 1, 1, 0. But I would claim that this is the same as this, because this is just minus iota. You can factor it out, 0, 1, 1, 0. This is effectively the same as a NOT gate, because this minus iota is a global phase factor that acts on any state that you give to it. And this global phase factor becomes immaterial when you make a measurement. So 180 degree rotation about the x-axis works as a NOT gate. And your original idea of a 180 degree rotation about the y-axis, you can work this out. Instead of x here, put a y here. And you will notice that your result will have a different phase for this iota and this term and this term, and it will not be proportional to this. So just do this as another homework. Try out finding out using this theorem of idempotent matrices whether the matrix form for a 180 rotation of the y-axis qualifies as a NOT gate or not. So you can look at this from the perspective of geometry happening on a Bloch sphere. You can look at this from the perspective of pure mathematical expressions as well. So a rotation operator really is defined in this form. So if you were to look at the Hadamard gate is a pi rotation about a twisted axis. Sigma x So x plus z and equal superposition. So let's write down the matrix for this. It's going to be e raised power minus iota something. So another way of writing this is exponent. So remember e raised power theta. Another nice way of writing this, if you are short of space and you don't want to make the line big, is to write this as exponent theta. Same thing. So this thing, according to our definition, is minus iota, pi is the angle of rotation. Now we need to have a combination of Pauli matrices. And that combination of Pauli matrices would be sigma x over 2 with an under root 2, because that's the cosine of the 45 degree of the x-axis, plus 1 over under root 2 sigma z with this factor of 1 over 2. And now you will work this out. The square of this is going to be proportional to identity. You need to find out what is the matrix here whose square is identity. So if I were to take sigma x plus sigma z, this is sigma x plus sigma z. Its square is, I think, identity. Is it? Or is it 1 by 2? This is 2, 0. So this is 2 into identity. So you need to put a 2 here, you need to put an under root 2 here, because its square is going to be identity. When you put an under root 2 here, then you have to add another under root 2 here, this becomes 1 over 4. So you have to put a pi over 4 here. But you just have to apply the theorem. Alright, so this is the matrix form for a Hadamard gate, and this matrix form will turn out to be proportional to this thing. It can carry any global phase, that doesn't matter, but it's going to be proportional to this. And when you factor out the common factor, you will get exactly this thing. Now, why is this a unitary gate? If I were, now I'm going to use R, any axis. So let any axis be denoted just by sigma. Any axis sigma on the Bloch sphere. Could be x, could be y, could be a combination, and some angle beta. Now if you want to undo a rotation, how do you undo a rotation? So you use the same axis of rotation and do a rotation by negatively same amount. So that will be undoing of the rotation. So if you look at this matrix, and undoing the rotation gets you back to the original state. So if you have a rotation operator and you want to find its inverse, which gets you back to the original, you just need to undo the rotation, do a negative of the original rotation. So if I take this rotation operator, every matrix, this is a matrix, we put inverse to this. This is simply putting a negative sign here. R, same axis of rotation, the minus beta. Now let's look at the matrix exponential form of just this thing, excluding the minus, excluding the inverse. Excluding the inverse. So this is e raised power minus I beta sigma over 2. Correct? So I'm taking the inverse of this. And what is this thing equal to? This thing equals exponent minus I minus beta sigma over 2, which is exponent plus I beta sigma over 2. So what's the relationship between this form and this form? It's just that we have inverted the sign of this iota. So it's just the complex conjugate of this. And all the Pauli matrices, if you look at the Pauli matrices, sigma x dagger is sigma 1, 1, 0. Dagger means you take the complex conjugates and transpose. So dagger is two things, complex conjugate and transpose. Transpose this, you get the same thing back. Complex on these are real numbers anyway. Look at this, sigma y dagger. You bring minus iota here, then take the complex conjugate, this ends up with a I. So this is the same as sigma y. Likewise, sigma z dagger is the same as sigma z. So they are self-adjoint. Pauli operators are self-adjoint. Adjoint is dagger. They're daggers of themselves. They're adjoints of themselves. So here, this thing will be the adjoint of itself, but this minus iota is replaced by plus iota. So this thing is really also the adjoint of this. Exponent minus iota beta sigma over 2 adjoint. An adjoint means complex conjugate followed by transposition. So a matrix whose inverse is its adjoint is called a unitary matrix. A matrix U whose inverse is its adjoint is a unitary matrix. In other words, you take a matrix U and multiply it with its dagger, with its adjoint, you will get identity. And you can do this in any order you like, because the adjoint is its inverse. You do a unitary operation and then you do its inverse, you get the same thing, you get identity. So all rotation operators are unitary matrices. So in the parlance of quantum computing, single qubit quantum computing, states are given by vectors, kets, pure states, and then rotation operators qualify as unitary matrices. Now the next lecture, we start looking at quantum algorithms. And for that we need to go up to 2 qubits, 3 qubits. We look at some important quantum algorithms. Now you have all the basics in place, just in 3 lectures. Do the homework, we're going to prepare a homework. So do the homework will be ungraded, but you have to do it. Alright, thank you.